This is your presenter Asloob Mudassar, and I am presenting slide number 127 of the course on laser physics. Question is, what is Q switching? What dynamics is involved in the process of Q switching? The answer is, Q switching is a process by which the quality factor of a laser cavity is raised to a very high value for a very high output power peak value. This is only possible when a laser system contains huge amount of energy by raising the population tremendously to an upper laser level. That is, the population inversion should far exceed the critical or the threshold population value and suddenly allowed to release this energy. To do this, a fast switching shutter is placed in a laser cavity. When the shutter is closed, the lasing action stops while the pumping process increases the inversion. Shortly, the inversion increases far greater than the critical value. When the shutter is opened suddenly, the stored energy is released in a short time in the form of an intense light pulse of the order of megawatt with a duration comparable to the photon decay time, that is of the order of nanoseconds. The process of Q switching can generate short but very high power pulses. Next, we discuss the dynamics of Q switching process. First, we describe how the inversion will change under a step pumping process. That is, the step pumping process is defined by this equation, that is Rp, which is the pump rate as a function of time, is equal to 0 for time less than 0. That is when we have not started the pumping process, the pump rate is 0. But when the pump rate has started, that is the time lies between 0 and the value Tp, then the pump rate is constant and is equal to Rp. Where Tp is the duration of the pump pulse. So you see that here the pump pulse has a duration Tp. The inversion behavior can be obtained from the rate equation. For example, for a 4-level laser system, we have this equation, that is dN over dt, that is the rate of change of a population inversion, is equal to Rp, that is the pump rate, minus B times phi times N minus N over tau. And the rate of decay of number of photons, that is d phi over dt, is equal to, or that is the rate of change of number of photons with time, is equal to Va times B times N minus 1 over tau C times phi. So these two equations have been discussed many times in the previous slides. So you can consult these equations for detail. By setting phi is equal to 0 and solving the upper equation. So if you set phi is equal to 0 in this equation, we have this equation, that is dN over dt is equal to Rp minus N over tau. And if you solve this equation, you will get N of t, that is the population inversion as a function of time, is equal to N infinity times 1 minus e to the power minus t over tau. You see that in this equation, that is in equation number 1 and 2, the parameters have been defined earlier, and I am going to repeat that one. N stands for the population inversion, that is the population difference between the upper laser level and the lower laser level. And you know that for a 4-laser level, the lower laser level, for a 4-level laser system, the lower laser level has a 0 population. So N is the population difference between the upper laser level and the lower laser level. RP is the pump rate, which has been defined earlier that it is a constant pump rate. So RP has a constant pump rate, and TP is the duration during which the pump rate will remain open. That is, the pumping process will continue for a time up to TP, because RB is a constant value. So the duration for this pumping process will start from the start of the laser, that is from from time 0 to time TP. B is the stimulated emission process cross section. Phi is the number of photons. N is the population inversion, and this tau is the lifetime of the upper laser level, or you can say that it is the spontaneous emission process lifetime. And here rest of the quantities are the same. This phi is actually the number of photons, and this tau c is actually the lifetime of the photon in the cavity. So tau c is the lifetime of the photon in the cavity. So by setting phi is equal to 0, in this equation, in equation number 1, we get this equation, that is a dn over dt is equal to rp minus n over tau. And if you solve this equation, you will get n or n as a function of tau, that is the population inversion. That is, the population inversion will varies as equal to n infinity times 1 minus e to the power minus t over tau, where n infinity is equal to rp times tau. So you see that when Rp is constant, then of course this infinity value, that is n infinity, should be constant if tau is constant, because the tau is also constant because the upper lifetime of the laser of the upper laser level is constant, and we are here using Rp as a constant value, that's the pump rate is also constant. So it means that n infinity is a fixed number. So these two numbers will decide the value of n infinity. So n infinity is the maximum possible value that could be possible for the population inversion to be achieved. So that's why it has been labeled as n infinity. This n infinity gives a asymptotic value of inversion obtained by setting t goes to infinity. So you see that here, if you set a t goes to infinity, then e to the power minus t over tau factor becomes 0, and then the population inversion as a function of time will approach the infinite value, will approach this n infinity value. So the population inversion, that is n of t, will give you the asymptotic value of inversion obtained by setting t goes to infinity. That is, n will increase from its initial value. For example, maybe from 0 value it will increase, and it will reach to the n infinity value asymptotically at a very large value of time. The time behavior of n of t and the fixed values of rp and n infinity have been plotted in figure number 1. So let me show you that figure first. So the caption of the figure first. Plot of the time behavior of population inversion as a function of time, that is n of t, versus time during the closed shutter in a Q switching process. That is, over shutter is closed, that is the laser the laser is not coming out from the laser source because the shutter is closed. But during the closed shutter, the pumping process will continue. So here we have set over two values. This is RP value. This RP value is a straight horizontal line, and this is a constant value. And this infinity value is also a horizontal line, and it is also a constant value. And you see that the population inversion n of t, that is as a function of time, will increase from its initial value, that is from 0. It should increase linearly along this curve. But you know that you can see that expression which it will follow, that is this equation. So according to this equation, the behavior is given, it will deviate it from the straight line, and you see that this is increasing according to our curve as given in equation number 3. So this will increase. But you know that when the time is very, very large, this population inversion will approach the n infinity value asymptotically. So here I have mentioned two times. One is tau, which is the lifetime of the upper state level, because you see that after this time, the decay of the population inversion will takes place. That is the laser from that is the population in the upper laser level will starts decaying after this time, which is the lifetime of the upper laser level. So this is what I have mentioned at the time. And the second is time is the tau p time. That is it is the time during which the pumping process, that is the RP value, is switched on. So in principle the RP value is up to this point, you see. But if you further increase the value of RP, so usually the pumping RP is done up to the point TP, because it is effectively increase the population inversion up to this point. But after that, the since the population decay will also takes place due to the lifetime of the upper laser level, so you see that the increase in the value of n as a function in the population inversion value will increase, but that will be at the cost of huge energy loss, because you are increasing the value of n as a function of time, but at the same time the population starts decreasing due to the upper lifetime of the laser is limited by the time tau. So RP has been shown as constant. The n infinity line, that is the maximum possible inversion value, is also constant, and this n of t, which will change with the time. As the time increases, the value of the n of t will also increase. And in theory, when the time t is very large, this n of t curve should approach asymptotically the value of n infinity. But in practical situations, this n of t will not approach the infinity values due to many reasons. One of the reason is that the upper laser level lifetime is tau is short as compared with the pumping mechanism, or up to the time tau p, during which the pumping for which the pumping time is for which the pumping process is done. So let me repeat again. So n infinity is given by rp time tau, and the value of the population inversion, that is n as a function of time, gives the asymptotic value of inversion obtained by setting t goes to infinity. The time behavior of n of t and the fixed values of rp and n infinity have been plotted in figure number 1. Tau is the lifetime of the upper state. When tau p is much greater than tau, any further increase in the inversion is balanced by the spontaneous decay, and the pump energy is wasted. So that's why I have said that it is not possible that n of t should approach asymptotically the value of n infinity. Theoretically, it is possible, but in practical sense, n of t will not approach to the value of n infinity, because the spontaneous process starts increasing, and due to that one, the population inversion starts falling. So the pumping, so a loss of energy is lost during the pumping process. So this is what, let me repeat again, when tau p is much greater than tau, that is when the pumping time is much greater than the lifetime of the upper state or upper laser level, any further increase in the inversion is balanced by the spontaneous decay, and the pump energy is wasted. One way to increase the inversion is to increase tau. So you see that if we want that this n of t curve, that is the population inversion curve as a function of time, should approach close to the value of n infinity, we need to increase this tau. So if tau is increased, it will lie along the axis of the time, maybe for example over here. Then you see that when tau is increased, the population, the spontaneous emission process is controlled somewhat, and then the population can still be increased. So one way is to increase the one way to increase the inversion is to increase the tau, which can only be realized when the electric dipole transition between the lasing levels is forbidden. So if we choose such materials in which the electric dipole moment, electric dipole transition between the lasing levels is forbidden, then for such levels we can have a time spontaneous lifetime of the upper state level of the order of a millisecond, that is at least 3 magnitudes of time greater than in the usual case, and in that case over population inversion, that is n of t could be made closer to the value of n infinity. And you see that when the population inversion is much greater, then of course a very intense beam, a very intense laser output beam can be obtained, or a very intense laser pulse can be obtained during the through the Q switching process. When the shutter is closed, that is, the no laser beam is coming out from the laser, but the pumping process is continued and the population inversion is being increased. So when the shutter is closed, the cavity loss gamma is high, which resumes its normal value when the shutter is suddenly opened at t is equal to tau p. So you see that this is the point. Tau p is the time at which we stop the for example, at which we close down the, at which time it is the time at which we open the shutter. So when the shutter is suddenly opened at t is equal to tau p, then you see that the cavity loss gamma will resume its normal value. The curve of the gamma will be discussed in figure number 3 probably. So bear with me and I shall explain the value of the trend of the gamma with greater detail in the next slide, in the figure 3. Due to fast Q switching process. So you see that our Q switching process is very fast. That is, we can open the shutter for an instant of time, that is very small in terms of time, and at the same time we can close the shutter very quickly. So due to our fast Q switching process, the presence of the term n over tau, that is which deals with the spontaneous emission of the population inversion, that is the decay of this population inversion through the spontaneous emission in the rate equation, can be neglected, because Q switching time is very short and is very fast. The qualitative behavior of n of t and phi of t have been presented in figure number 2. So let's look at the behavior of the population inversion and the increase in the number of photons in equation number 2, in figure number 2. So this is figure number 2. So let me first of all describe the caption. Plot of the time behavior of the population inversion with the time, that is n as a function of time versus time after the shutter is opened in a Q switching process at t is equal to Tp. So t is equal to Tp is the time at which the shutter is opened. So when the shutter is opened, a huge pulse of the laser output is obtained from the laser source. And this is what is being described by this figure. So you see that I am plotting n and phi along the vertical axis and t along the horizontal axis. And I have shown 2 times tau p at which the shutter is opened and 2 tau t. So you can see that Ni is the initial population inversion. Just when the shutter is opened, the population inversion that was present was Ni. So that is why it is called initial population inversion. So you see that soon immediately the population inversion starts decreasing, because we have opened the switch. Now the stimulated emission process will dominate, and you see that there is a huge and drastic fall in the population inversion. So this curve you see that show a huge fall in the population inversion. So when the population inversion falls very quickly, it is accompanied by an increase in the number of photons in the cavity. So phi of t will start increasing. So you see that it will increase after some delay, because the population inversion will also start decaying after some time, because it stays constant for some time and then it starts decaying. So at the same time, the number of photons in the cavity starts increasing. So when the decay of the population inversion, the decay reaches to the value critical inversion. At the value of the critical inversion labeled with NC, then of course what happens? The absorption, the stimulated absorption, the stimulated absorption action starts, and the absorption through the stimulated process of starts taking place, and the number of photons will then will fall, because the number of photons will start being will be also absorbed by the stimulated absorption process. So you can see that the peak of the number of photons will increase up to the value when the population inversion stays above the value of the critical population inversion, and at the point of the critical population inversion, the number of photons has reached its maximum or the peak value. And when the population inversion decays below the value of NC, that is the starts below decay, that is n of t falls below the value of NC, then of course the number of photons starts decaying, and then ultimately when the population becomes very small, then of course the number of photons become nearly equal to zero. And this number of photons, you see that is peaked at a value when we have 2 times of tau p. And then you see that the population inversion reaches its value, its minimum value, which we call as NF, the final population inversion value, which stays as the background population inversion in the cavity. So let me complete the description over here. So the qualitative behavior of n of t and phi of t have been presented in figure number 2, which I have discussed. At t is equal to tau p, the switch is opened and the inversion available at that instant of time is regarded as Ni. So you see that at the time t is equal to tau p, the switch is opened and the initial inversion is recorded as Ni, which can be obtained from equation number 3 by setting t is equal to tau p. So if you set t is equal to tau p in equation number 3, that is, if you set t is equal to tau p in equation number 3, you can get the value of n of t to be equal to Ni. The inversion stays constant for some time and then starts decreasing, which you can see from this plot, that inversion stays constant for a short interval of time and then it starts decaying, and then it starts decreasing. The photon numbers at the same time starts increasing and reaches its peak value when the inversion has fallen to its threshold value equal to NC, which you can see from this plot. That is, the number of photons increases up to the value when the population inversion has decayed to its critical value. There you can see that the corresponding peak in the number of photons can be seen. Okay, at n of t is equal to NC. So this is the point where we have n of t is equal to NC. The net gain and the net losses balance each other. So the critical inversion is the point where where the net gain and the net losses balances each other. Beyond this point, net losses become greater than the net gain. So when you go below the point of NC, the losses becomes greater than the gain. So beyond this point, the net losses become greater than the net gain and the photon number starts falling and eventually approaches zero. So you see that if you could, the reason to explain the decay in the number of photons on this one is due to that that the number or that the cavity loss becomes greater than the gain in the medium. So beyond the value of the critical point, you can see that beyond this point, the net losses become greater than the net gain and the photon number starts falling and eventually approaches to zero. During the time, the inversion keeps on falling and reaches its final value NF, which then acts as the background inversion left in the active medium. So NF is the background value left in the active medium. The time during which the shutter remains closed is decided by the upper state lifetime, and the time during which the shutter should remain open for Q switching is decided by the photon decay time, that is tau c. So tau c will decide for how long the Q switching shutter should remain open. So it is the tau c or the photon decay time will decide. So let me read again this paragraph because it is important. The time during which the shutter remains closed is decided by the upper state lifetime, that is tau. So this tau will decide that for how long the shutter should remain closed. And the tau c, where is tau c? Tau c can be seen in this equation, for example, this one. That is the lifetime of the photons in the cavity, and this lifetime tau c will decide for how long the shutter should remain closed. In case of slow switching, the cavity loss gamma as a function of time decays slowly. So in the slow switching, that is if the switching process is slow, then the cavity loss gamma as a function of time decays slowly. This will be explained in the next figure. So this is the next figure. Let me explain this figure first. And then the caption of the figure: occurrence of multiple photon pulses in a slow Q switching process. So when the Q switching process is slow, then you see that multiple photon pulses could occur. For example, here in this particular example, two pulses will occur in the Q switching process. You can see that I have plotted gain, net gain, and the net loss gamma, net gain G and the net loss gamma along the vertical axis, and I am plotting them as a versus time, which is time along the horizontal axis. So let's concentrate on the first gamma of t. So you see that gamma of t is slowly decaying along this curve. So it is decaying, you see, gamma of t. What about G of t? That is the net gain. Look at this net gain. Net gain is constant initially. And initially, the net gain is lower than the gamma of t. That is, the net gain is smaller than, has a value smaller than the value of the losses in the cavity. So the gain in the cavity is smaller than the losses in the cavity before the time t1. So after the time t1, the net gain becomes greater than the loss. And this is the process you see that during which the number of photons will be available in the cavity, which you can see that between the time t1 to t1 prime, the number of photons are increasing in the cavity. It means that the photon pulse is being contributed up to the and the contribution will remain valid when G remains greater than the value of gamma. That is, the gain becomes stay greater than the value of the losses in the cavity. And this is the time between T1 and T1 prime. So you can see that the photons in the cavity are being contributed because the gain is greater than the losses. But you see that at this point, which corresponds to T1 prime time, after that, the losses becomes greater. The net loss becomes greater than the net gain in the cavity. And then you see that you can notice that the photon will decay. So the photon will decay and becomes zero. So this is the process at which pulse 1 will takes place. So the pulse 1 will emitted between the time after T1 and is peaked at a time T1 prime. So after that, if you will keep on concentrating the gain curve, you see that the gain curve then stays constant. So no process is decays constant, but lower than the value of the net losses. And you see that after at a point T2 and beyond the point T2, what happens is that the gain becomes greater than the loss. So G becomes greater than the gamma curve. So this is the time at which the number of photons will start contributing in the cavity. And a second pulse can be seen between the time T2 to T2 prime. And at the time t2 prime, again the gain falls below the value of the losses, net losses in the cavity. That is, the value of g function becomes lower than the value of the gamma functions, and then you see that the number of photons starts decaying and becomes zero. So in this way, you can see that the two pulses, one after the time t1, and the pulse is peaked at t1 prime, and the second pulse starts occurring after the time t2 and is peaked at t2 prime. So these two pulses will occur. But you see that multiple pulses can also occur in the Q switching process, provided the gamma curve starts from the very top, and also the gain also starts from the very top. And you see that if the gain is very high and the losses are very high, then of course multiply the gain could be greater than the net losses at multiple times, and then of course multiple peaks can be seen at in this curve. In this present curve, only at the two instances the g becomes greater than the value of gamma, so two peaks can be observed, one after t1, the other after t2, and the peaks of the photons will be observed at a time t1 prime and t2 prime, because after that the losses in the cavity, the net losses in the cavity becomes greater than the net gain in the cavity. The time behavior of the single pass gain. So you see then in the quick switching process, mostly the single pass gain is involved, because the Q switching time is also very small, that it will allow most of the population inversion will decay during the single pass gain. So the time behavior of the single pass gain, which is given by g of t, which is equal to sigma times capital N cap and small and times n, L. So g of t is equal to sigma times n times L, where L is the length of the active medium, capital N is the population inversion, sigma is the stimulated emission cross section, which we are considering same for both stimulated emission and stimulated absorption. So g of t given by this one along with the photon and along with the photon number phi of t are also shown in figure number 3, which I have explained. The gain due to saturation decreases at 2 points, T1 prime and T2 prime. So T1 prime and T2 prime are the 2 points at which the gain due to the saturation decreases. The first pulse of phi of t starts at T1, where the decreasing loss becomes equal to the gain. So you see that T1 prime and T2 are the prime where the loss and gain becomes equal to each other, where the net gain and the net loss becomes equal to each other at time T1 prime and T2 prime, and after that the number of photons starts decreasing. Phi of t then reaches its peak value at T1 prime and T2 prime, because initially from T1 it starts increasing, and similarly after T2 it will start increasing, and it will peak at T1 prime and T2 prime, and after that it starts decreasing. So phi of t then reaches to its peak value when the falling gain becomes equal to the loss. The second peak in phi of t similarly follows after T2. So you see that I have explained very shortly the process of the Q switching process, and the parameters on which it depends, and the parameters which can be helpful in controlling the Q switching process. And you know that in the Q switching process, the purpose is to obtain a very high power short pulses, a very high power short pulses. Usually it is aimed to obtain at least one pulse. So if the Q switching process is a slow process, then multiple pulses can be obtained, but the first pulse will be the highest in peak. So this is the end of slide number 127.